So okay, so this is the first session. So we'll be discussing a little bit about AI/ML. What was the vision behind starting of paying forward community AI/ML? And second session about 30 to 40 minutes would be by Bibek, and last 15 minutes will be a question and answer session. So let's start with AI/ML community. So the vision behind AI/ML community is that, like in Nepal, we don't have a place, right, where we can learn about, where you can connect about data science. So we want this to be a platform where if you have any issues, let me say you are doing some projects on multi-level classification, and that might be a bit tricky because you don't have a lot of research paper on multi-level classification. It's a very difficult topic. So we want it to be a place, and there might be few people who have already worked on that. So we want it to be a place where you can put your queries on Slack channel. We are starting with Slack because we have seen that Slack is mainly used by professionals. That's the reason we're not going with Facebook groups and everything, because we want this to be a place where professional people are together. They can help each other, right? So the example I was giving in multi-level classification, because even in our case, sometimes when I have a multi-level classification, there are not a lot of research paper and tutorial on that. So what people might have already worked on that. So we want it to be a place where you can put your questions and someone can guide you, right? Saying that, okay, these are the things I have tried. You guys can go down this path and see how it goes, right? That is one thing. Second thing is we want to connect, right? We There are a lot of competition happening out in the world, and we need a group of people working together, like-minded people working together, either to compete or either to brainstorm. And we don't have a platform for that. So that is the reason, like that is supposed to be a platform where people can work together. And third one is there are a lot of job opportunities and other things over there. So we want to make sure that different companies can post their requirement. You guys can show your skill and then have one platform where people can do the hiring and everything. And third part is always learning, because we can learn from everyone, from who is just starting to who has one in this industry for more than like 10 or 10 years. Not before that. I think like data science has been there for only about 10 years. So because of all this reason, we have started a community. We are starting with the talks, but this is just getting started. We'll have different kind of challenges in place. We'll make different groups who can compete in Kaggle or other competition, right? So basic idea is to make sure that this is one place where you can learn new things, you can collaborate, you can look for the jobs, show your portfolio, so that you can connect with like-minded people, right? So that is on overall about AI ML community. And if you guys are interested in giving a talk like this one, please let us know on the chat, right? So you can contact anyone on the code member. You already have that list on the website. You can go to the website, see the list, and then ping them on Slack. We are always available. Like we always check the Slack channel every day. So if you are interested on giving talks, or if you guys have some issues, then post it on, ask me any ask for help so that people can help. If you have some interesting article, then put it on that research group or article group so that other people can also learn from it, right? So that is the overall idea. Anyone else on the core member you guys want to add, if I have missed anything regarding the vision of AIML? Okay, then let's get started. Let's start the talks. Like we have already started the recording. So today's talk is by Bibek. Bibek. So one of the is, and I'll be one will be monitoring the talks. So basic idea is we want this to be interactive sessions. So you can ask here. You'll be muted during the talk Bibek is giving, but you can always put your questions on the chat. And once Bibek's talks is over, we'll unmute so that you guys can unmute and ask question directly, because I think that is the best way more than answering a question. But if you have any questions, then you can put it on the chat and we'll pick it up. And as per Bibek's availability, we'll make sure that we ask that question, right? So the reason for why did we choose this talk today is that there's one thing you guys might have heard a lot. 80% of deep learning data science or machine learning project never go into production, right? That is a fact, right? And one of the major reason for that, there might be a lot of reason, but one of the major reason for that is it's very difficult to deploy, because you might train a very big model on GPU, CPU, but like deploying it is a very big part of it. And if the model is really large, then ROI for deploying that model can be really tricky. And things are getting larger and larger. So because of that, we need to figure out a way to compress that model so that the prediction can be done on device, it can be done on very low hardware resources, right? So that's a very interesting field. Bibek will give more idea regarding where it is going and everything. But that's the context, and that is a very interesting topic for all of us. So that's the reason I have chosen that as a first topic. So I'll let Bibek take over from here.
Okay, thank you, John. Let me start by sharing the slide then. Okay, so I am assuming that everybody can see my slide.
Yeah, we can see.
All right. Okay. So yeah, welcome everybody. Greetings from my side, from wherever you are joining. And I think you already know that today's topic is model compression slash on-device AI. So I am not gonna like talk completely in detail about like model compressor and on-device AI, because it is like a very broad topic. What I want from this talk is that I want you guys to take away the intuition behind model compression and on-device AI, that okay, oh, there are something like this in this field. So if you can do that, I think this talk is going to be very successful. So just to start, let me start by like my introduction. So I graduated from Yonsei University, which is one of the top university in Korea. And I graduated in 2019 with a degree in mechanical engineering. And after that, right after my graduation, I joined an on-device AI startup called Nota. This is also located in Korea, in Seoul. And I have been working there as a research engineer since 2019. So you guys might wonder, like, okay, this guy majored in mechanical engineering, but how did he ended up in working in AI? So just to give a little bit background, what happened is like, there was a time when AlphaGo, like this thing, AlphaGo versus Lisa Dole, this thing happened in Korea. So, that thing like was so big that after that event, wherever you go in Korea, people were talking about AI and, machine learning and robotics and this and that. So, there was a different kind of hype about AI. So that's the hype, where I also got in and I got interested in about AI. So by the time I graduated, I decided to pursue a career in AI and not in mechanical engineering. And I'm pretty happy with that. So that was the background. So that was about me. And I also made some assumption about you guys, the audience. I am assuming that you are a technical audience. And what I mean by technical is that you know the basics of AI, machine learning, a little bit of like linear algebra, for example, what is, SVD, singular value decomposition, just the basic stuff. And you know what is like neural network, what is CNN, and maybe you have some experience with like training models, and like what is forward propagation, what is backward propagation, and just the very basic stuff. So even this is just my assumption. Maybe some of you guys know more about this, maybe some of you like know less about this, or maybe some of you are just not a technical audience, you are just someone who wants to learn about this field and are just starting out. That is completely okay. But so for those of you guys, I think this talk would be like, a talk where you can like get some keyword, like for example, CNN, neural network, AI, this and that, and you can take those keyword and Google and start your learning process. So that's my assumption about you guys, that you are, to a certain extent, a technical audience. All right, so this is going to be the content for today. I will be talking a little bit about the recent trend in AI, and then we'll talk about the cloud AI versus on-device AI, the plus and minuses of the both AIs, and then we'll talk briefly a little bit about on-device AI, and finally, the main topic, like I will be talking about the model compression techniques, the techniques that you can use to compress AI models. Okay, so right. So the recent trend in AI, is that deep learning models, they are getting bigger and bigger and bigger. Like, when CNN first came out, the number of parameters in AI model were like in terms of thousands, and then from thousand it became millions, and from millions it became billions. And by the end of last year, there we had a few numbers of trillion number of parameters in AI models. So, and this trend is just gonna continue. I don't see this trend coming to an end, because the more number of parameters you put in the model, the performance get better, like the capacity of the model, increases. So like top tech companies like Google, Facebook, OpenAI, they are just, putting in a lot of parameters in AI model and just increasing the number of parameters, increasing the size, and this trend will surely continue. But these big models, they come at a cost, and the cost is the computational cost, as these models gets bigger and bigger and bigger, the amount of compute that you need is also very expensive, because you cannot train these models on a normal GPU servers, or just some like normal GPUs. You need like next level of compute, and those level of compute, they also come with cost, like in terms of money. For example, GPT-3 was a model released by OpenAI last year, and it made a lot of headlines. And one of those headlines was the amount of money that went into training GPT-3. So, if you were to replicate GPT-3, on a Tesla V100 CPU, it would take a lot of time. Some people estimate that it's going to take like roughly 355 years just to replicate that model result. And that was just in terms of time. Talking about the money, it's like $4.6 million, is you need it just to train one big model. So there is definitely a lot of cost that goes into, when you're increasing the number of parameters. So that is one. And the second thing is because these models are like super big, like super heavy, very have a lot of parameters, you cannot just take this model and deploy it, so the deployment process itself is also very hard. But let's say just in case you end up deploying it, you can only use cloud for deploying, because it is just too big that you cannot deploy it on the device. You have to use the cloud, and because of its size, there will be like another cost that's going to come with cloud. So first, the cost is in terms of training and also the deployment. So those are like the two things that comes with like bigger models. So for bigger models, like when you use cloud AI for deployment, it is good, but the thing is there are some problems, when you use cloud AI to deploy your model. So the first is gonna be the computational cost. In this time, this cost is related to deployment cost, because when the training is done, the training itself is very expensive, but when the training is done, you deploy it. So as long as the model is deployed on the cloud servers, you have to pay, for example, maybe to Amazon AWS, you have to pay the cost. So there is cost in that. And the second thing is going to be latency, because your model is deployed to the cloud, and you want to and your phone uses some kind of app application that uses that model. So what happens is your data will have to go to the cloud, and then we'll do the inference in the cloud, and the result is going to come back to your phone. So this time, the data leaving your phone, going to the cloud, coming back, this is also going to take some time. For for us, like in normal scenarios, this latency might not be an issue, but think of like very extreme applications like self-driving cars, you know, like this, even like the fraction of millisecond can result in somebody dying, you know, because like the time to react is just it's just nothing, you know, it's just a very, you know, it's very minor. So like this latency could be an issue in those extreme applications. And the final issue with using cloud AI is privacy. Like your data is leaving your phone and is going to somebody else's cloud, you know, this thing, I mean, at least for me, I mean, it's something that I just wish, you know, can be solved, you know, because you cannot trust your data, your personal data to somebody, you know, you just want, okay, this is my phone, this is my device, I want my data to be here, I don't want it to leave, you know. But bigger models, the models that are deployed in cloud, you know, they just the companies, they have access to your data because, you know, you were using their applications. And so these are the two main issues with using cloud AI. So all these issues, all these three main issues can be solved if you are using like on-device AI. So let's say your device, your AI model is deployed on the device. So because it is deployed on the device, there is literally no computational cost, like because you don't have to pay for the servers for deployment because it's already deployed on the device. So, you know, it's gonna help you a lot in terms of computational cost and latency, because like everything happens on device, latency is also super fast. And privacy, again, because the model is there, the data is there, like whatever happens on your device, nothing goes out of your device, so there is no privacy issue. So these are the three big minuses of cloud AI are the three big pluses of on-device AI. So you might think, okay, on-device is good, but like, does it have like really practical applications? Are there like companies working on it? Are there like, you know, what's really happening in the industry? So just to give you you know, a little bit of idea of what's happening like in this on-device AI field. So there was a company called Axnor.ai. It is like probably one of the first and well, one of the best like on-device AI companies. So they had like you know, AI models for different applications, and you know, they could run them like very fast on ASD voice AI. So what Apple got interested, you know, so Apple they just bought it, Xnor AI, and this happened roughly like in 2019, late of 2019, early 2020. And they bought it for like $200 million. So definitely there is a lot of value generated from like is AI on device AI. This is why Apple bought it. So and also recently the company that I work for, Nota, we raised roughly like $14.7 million in our Series B for like our on device AI technology. So you can see there is tremendous amount of value that is being generated with on device AI. This is why like investors and companies, they are just pouring their money into this technology. And also there is a company called like AIML. This is like an American company. They also, you know, raised a lot of money recently in their Series B. So companies and startups, they're raising money. And also there is a Canadian startup called DeepLight AI. They also raise money. And these are just like the few main, you know, main topics, main companies that I brought here. Except this, the lot of like on-device AI in all around the world, even in Korea, we got a lot that are like primarily focused on on-device AI. Even the big tech companies, they might not be focused mainly on on-device AI, but a part of their division, I'm pretty sure, is working on on-device AI. So this thing is very important and is generating value. So like on-device AI, we can just from the name, we can think of it like a device plus AI. So a device is going to be like hardware plus software. So you can do like on-device AI just from a hardware perspective. So, you know, instead of like you are not doing anything for like on the software side, what you are doing is like you are just making specialized hardware that will run your AI models faster, you know. So like a normal hardware is going to take a lot of time, let's say, to do inference, whereas specialized hardware, you know, that are like optimized for like AI models, you know, you can use that to do like, you know, to speed up your inference speed. And NVIDIA has like some really good like hardware devices that's out in the market, and like there are a lot of companies that are working on like making specialized chips. Even Samsung, they're working on it. So you can do just like on device AI from a hardware perspective. And then there is a software perspective. So from the software side, what you can do is like you can do model compression, and then you can take that model compressed model and then do the optimization. So the pipeline is going to be like this. So you got an AI model, and then what you can do is like you can do compression, and then you can do optimization. Or what you can do, you can just do AI model and then do optimization. This is correct as well. So like from my side, what I think is the overall AI on device AI pipeline is like your first you need an AI model, so you have to do modeling. And the frameworks that you can use to do modeling are like PyTorch, TensorFlow, Paddle. Like this is a framework from Baidu, from a Chinese company, and then we got the new framework coming from Google. It's called Zax. So these are the things that you can use to train your AI model and do modeling. So once you're done with this, what you can do is like you can do compression. Take this model and then do compression. And the techniques that you can use to compress your model are, like these are the main techniques that are used to compress the model. The first is like the tensor decomposition, pruning, knowledge distillation, nonce, quantization. So these are like few techniques that you can use to compress your AI model. And then you can take this compressed model to do optimization. So the best optimization, the best example of the optimization toolkit is like TensorRT. So it is an optimization toolkit that's from NVIDIA. So it is really good. Like if you wanna just take a model and then kind of optimize it for the hardware. So TensorRT is one of those, like TensorFlow optimization toolkit is another. There is something called like Megxin from Megpy, another Chinese company. There is something called NCNN, it's also an optimization toolkit from Tencent. So like, you can use these tools to do the optimization thing. And finally, when your model is compressed and optimized, you can take the model and then deploy it to your to your hardware. Yeah, the hardware could be like some NVIDIA IoT devices, could be Raspberry Pi, could be drones, could be mobile phones, yeah, depending on your applications. So this pipeline is something that I would say like is an end-to-end pipeline for on-device AI. This is how most of my work is done. I start with an AI model, and then I apply some compression techniques to compress the model, and then I do the optimization, and finally I deploy it. But so this is the case for me. But like what you can do is like let's say you don't know anything about compression, you just know a little bit about optimization, so you can just take an AI model and go like skip the compression part and just go to the optimization. You can do that too. Or you can just like take the AI model, compress. If you know a little bit about compression, you can compress it, you skip the optimization, and then go to deploy part. That is good too. But the thing is, if you go like step by step AI model, compression, optimization, and deploy, I think you're gonna get the best model, like the model that is like super fast and it's super light. If you go like step by step, of course you can skip like 1 or 2 steps in the middle, but I would recommend you to go like step by step. So this is the pipeline that I use for my work, and most of my work is concentrated around compression, and this is what I will be talking about today mainly. So the first topic of model compression is called tensor decomposition. So it's a technique that you can use to kind of compress your model, like especially reducing your parameter size. So what happens in tensor decomposition is like let's say like your neural network contains your neural network contains a lot of layers with CNN. So CNNs, they have weight matrices, right? And let's say the dimension of the weight matrices is given by CK. So total the number of parameters that this weight matrix is gonna will have is gonna be C squared, K squared. So that is like the normal scenario. But what you can do is like you can use low rank approximation, like from linear algebra. You can and you can like, instead of using this square matrix, what you can do is like you can kind of decompose it into some like into rectangular and into a rectangular and horizontal matrix. And one dimension of this approximated matrix is going to be the same, but the other dimension is going to be some r, which is like which is less than ck. So this is going to give you roughly the approximated version of your original weight matrix. So if you do this, the performance is of course there is a little bit decrease, but the approximation are are kind of like it's something that you can afford. Yeah, so there is not a lot of performance decrease, but just by doing this, you're reducing a lot of parameters, like your parameters from like c square k square is down to 2ckr. So this is like one of the popular techniques that is used to kind of reduce the number of parameters. So you can also think of tensor decomposition as like taking an operation that is expensive. So instead of like doing that expensive operation just at once, why not like break it down into two or like, you know, a number of steps which are like computationally not expensive, which are computationally cheap. So I will like say it again, like tensor decomposition can be you can think of like tensor decomposition as something that taking an expensive operation and then breaking it down into computationally cheap operations. So one great example of this is like, you know, this concept was introduced in MobileNet. So what they did is like they kind of take standard convolution, which is like computationally expensive, and they kind of like factorize that in standard convolution into depth-wise and point-wise convolution. So this is the paper that I was talking about. It's called like MobileNet. It came out from Google. So this is the roughly this is like a standard convolution. So you got like dk by m is the dimension, and n is the number of channels. So this is how the number of parameters is in terms of a standard convolution. So what they did is like, instead of doing this normal convolution, the standard convolution, they went like two-step. Like let's do depth-wise first. So what they did is like they from m they kind of reduced the width of the channel to 1. So they just did like convolution just per channel, and then after that in the second step after that what they did is like this time they took the result from the depth-wise convolution, and then they increased the number of filters to m. But this time they reduced the dimension of the kernels. This time they just use 1 by 1. So just by breaking this standard convolution into a series of two computationally cheap operations, they were able to reduce the number of parameters like from 29.3 million to 4.2 million. That is a lot of decrease in the number of parameters. And this is just the number of parameters. And also they were able to do because these two operations like depth-wise and point-wise convolution, they are like computationally cheap. So you can see this thing here as well, like the standard convolution, they require like in total 4,000, roughly like 5,000 numbers of like multiplication and addition. So this one was reduced to just like roughly 600 operations of multiplication and addition. So this is also like it's going to help you in terms of compute. And of course, because standard convolution, you are like breaking it down into into computationally cheap. But this depth-wise and point-wise is not 100% approximation of the standard convolution. So this is why there was a decrease in the performance. I like my personal opinion is like this decrease is kind of acceptable if you're given the amount of gain you have in terms of operations and in terms of parameters. So this is like MobileNet is a great example of tensor decomposition technique. I have put a link. Those of you who are interested, you can read more about this paper. Okay, so second one is called pruning. So pruning is about removing redundancy from the network. You know, so you got a neural network, and the main like principle of pruning is that not all parameters are created equal. Like a neural network is going to have a lot of parameters. And if you just think about it intuitively, like not all parameters are created equal. Some parameters are going to be more important to the network. Some parameters are going to be less important to the network. So what pruning does is like, let's keep the important parameters in the network, but let's remove the less important parameters from the network. So this is what pruning does. It basically prunes the parameters that it thinks are not that important to the network. So there are like two types of pruning. The first is called unstructured pruning. The second is called structured pruning. So what happens in unstructured pruning is like only weight pruning is done. So what you are doing is like you are taking some pruning algorithm and which decides, okay, this weight parameter is more important, this weight parameter is less important. So the parameters that are decided as less important is pruned. So the way pruning is done in unstructured pruning is, basically weights are going to be inside the matrix. So your pruning algorithm decides, okay, this weight is not important. So pruning is done by just making that weight, that parameter 0. So you got a big weight matrices, and like, let's say a certain portion from that weight matrix are just made 0. So what happens is when you got a lot of zeros inside a matrix, that matrix is called a sparsified matrix. So unstructured pruning does sparsifies the network via weight pruning. So in terms of like picture, what you can think of the weight as the connections between the neurons. So unstructured pruning takes like unimportant networks and just prunes it. So these dotted connections are pruned. So this is good, but the thing is, this kind of pruning requires specialized hardware to actually experience the speed up. So you can do the pruning in an unstructured way, but the thing is, because nothing really is removed like from the network. What happens is just like you are taking some weight parameters and making those parameters 0. So the multiplication cost, the operation cost is going to be there. Like even though the element is 0, the cost is going to be there. So you kind of need some kind of specialized hardware that supports those sparsified operations, so that you can actually see the speed of so that you can actually experience the speed gain via unstructured pruning. So this is like one way of doing pruning. The other way, and the way that I mostly use in my work, and I think is the kind of pruning that is widely used in the industry, is called structured pruning. So what happens here is like you are just completely removing the channels or the layers that are decided less important via pruning algorithm. So let's say if your pruning algorithm decides that, okay, this channel or this layer is not that important to the network, then that channel or layer is completely removed. So like let's say your convolution layer, like before it has like 64 channels, and the pruning algorithm decides like, let's say half of it is not important. So like 32 of those channels are completely removed. So from 64, it became 32. So because like the overall structure of the network stays the same, what happens is just the reduction in the number of channels or layers, and that happens completely very structure wise. This is why the speed up is like it can be experienced on any hardware. You do not need some kind of specialized hardware to actually see the gains of structured pruning. So if you're doing pruning, unless you have some specialized hardware, I would recommend you to go for like structured pruning. Okay, so I was in the last slide, I talked a lot about like pruning algorithm. So let's talk about that. So by pruning algorithm, what I mean is like algorithm, they kind of define the criteria of pruning, and what the criteria really represents is like how important is this parameter or channel or layer, because pruning is about keeping the important ones alive and then kind of like killing the less important ones. So you need a criteria, a cut line that, okay, everything above this cut line is important, everything below this cut line is less important. But that's how you do the pruning. So there are like a lot of popular criterions that are used to do the pruning. Like there's something called like L1 norm, L2 norm. You can use like L1 norm of the weight matrices as a pruning criteria and give a threshold. Everything above this threshold is okay. Everything below this threshold becomes 0. So that is like one way of doing it. And another popular pruning criteria is called Bayes normalization scaling factor. So I think a lot of you probably they know this thing. When you have a CNN layer, you have Bayes normalization that is just followed by CNN layer. So if the number of channels in the convolution layer is 32, you got 32. You got the same number of scaling factors in the Bayes normalization layer. So one of the paper, what they did is like they took the values of the scaling factor as a pruning metric. So if in the figure, as you can see, these scaling factors, they are like kind of they will have values. So they also had like some threshold. So let's say if the threshold is like 0.1, so everything below 0.1 is going to be pruned, and everything above 0.1 is going to be there. So in this thing, like these things, that the values are true-less. So depending on this value, the channel in the convolution layer, they are pruned, and and the and the remaining ones are shown here. So this is like just one paper. We have a lot of paper about pruning criterion. So I would, if you're interested more, you can look it online. So that one was about the types of pruning and the pruning criteria. But like, how do you actually do pruning? Like, when is it done? So the first way you can do pruning is something called like one-shot pruning. So you have like a pre-trained AI model, and then you can take that model and then use some pruning algorithm to do the pruning, and then you can take that pruned model and do fine-tuning. So well, the reason you do fine-tuning is because when you do the pruning, you are like basically removing some of the parameters, some of the channels and layers from the network, and that is gonna cost performance. Like the performance is gonna drop a bit. So in order to recover that performance, you do fine tuning. You kind of take the pruned model and you retrain it one more time with your data. So this is like is one shot pruning, because you're doing pruning just one and at once. And the second is called iterative pruning. So it is similar to one-shot pruning, but what you do is like you do pruning again and again. You got an AI model, you do pruning, you fine-tune it, you take that fine-tuned model again, and then you prune again. You take that pruned model, fine-tune. You do it until your condition is satisfied. Until you are satisfied with the number of parameters or the number of computational operations. Until you are satisfied with that, you do the pruning again and again, iterative. And then there is something called like pruning await training. So the what happens here is like you have a model, and you do the pruning in such a way that this you do the training in such a way that this training is gonna help your pruning later. So you kind of know that I'm going to prune this model later. So when I'm training it, why not train it in such a way that this training process is going to help me later when I'm doing the pruning. So if you're doing it if you're doing the training in a way that is helping your pruning later, it's called pruning away training. So you get an AI model, you train it in a way such that it is helpful to pruning later, and then when this training is done, you take that model, you do the pruning, and then you do the fine tuning. So in my previous slide here, so in this paper, what they did is like you have a normal CNN network, let's say. So they did not just use this better channel scaling factors just like that. What they did is like they trained it in a pruning aware way. So what they did is like they trained the network with L1 norm regularization on the scaling factors of best normalization layer. So the property of L1 norm regularization is that it kind of makes the important element more important. It kind of makes the less important element less important. So if you see here, the important ones got like very important, the less ones, they become very less important. So this is how they first trained the network in a pruning aware way. And then when the training was done, they took these scaling factors and had a threshold. Depending on the threshold, they pruned the networks. So this paper is actually a great example of pruning away training. Yeah. Okay, so and then the way you do pruning is like, for example, you need to do pruning. So for the first thing that you need, like you need a pruning algorithm, and you also need some kind of percentage. Like, okay, I want to prune this percentage from my network. So let's say. So if you have that, so there's something called like global pruning. So let's say if you have like a 3-layer of neural network. So in this thing, let's say you want to prune like half of the parameters. So what you do is like you just give like, okay, I want my pruning ratio to be 0.5. So the pruning algorithm is going to decide like how much is to be pruned from the first layer, how much is to be pruned from the second, how much is to be pruned from the third. You know, this is this allocation of pruning ratio is going to be decided by the pruning algorithm. So for example, you know, because it is 50, maybe like it could be, you know, the first layer is like it's going to be pruned like 30%, the other is going to be pruned like 10%, the other is going to be pruned by 10%. It's so in total is 50. So every layer they kind of have like different pruning ratio. So this way of doing the pruning is called global pruning, because you are just giving the pruning ratio, and the pruning algorithm like on its own, you know, kind of divides that pruning ratio into overall network. So this is called global pruning. And the second one is called local pruning. So here, pruning is done locally. And what I mean by that is like the pruning ratio for every layer is the same. So let's say if you're saying like, okay, I want 50% to be pruned from all the layers of the network. So like for every layer, the pruning ratio is going to be the same. The first layer, like 50% of the parameters is going to be pruned. The second layer, the same. The third layer is the same. So this is like two ways of doing pruning. You can do it like either globally or either locally. And if you ask me like which one is good, well, it kind of depends like on the kind of network that you are using, on your applications, whether like it is classification, detection, segmentation. Depending on that, global could be good. In some cases, local could be good. But personally, I prefer like global pruning, because this allocation of this thing, my personal opinion is that it's not good. Like for example, not in the beginning of the pruning slide, I said like not all parameters are created equally. So in local pruning, like every layer, like you know, half of the parameters they are like pruned like every layer. So what they are assuming in local pruning, that every layer is kind of same important, which is not the case. Some layers are definitely more important. So in those layers, like less pruning should be done. Some layers are less important. So in those layers, more pruning should be done. So this is why I prefer like global pruning is better. And to be honest, like it actually gives like better performance compared to local pruning. But like in some cases, local pruning is better. So yeah, you need to experiment. So I brought like a little bit of table about just to give you like what pruning can do. So this is a popular model called Yellow V5. It's like one of the state of the art of detection models. So like original YOLO V5, they had darknet as their classification backbone. But in this experiment, what happened is like they replaced the darknet with MobileNet V2, and the MAP was like this, was 71.9% was the MAP. So the pruning algorithm that was used here is the same that I presented before, like the best normalization scaling factor. So if you want to use that thing, you first have to train it in a pruning aware way. And the training was done with something like this is the factor that is used to induce L1 norm regularization on the scaling factor. So first you have to take the original model and then induce it with like L1 norm regularization, and this thing is going to be added to the loss of the network, and you know the overall training is going to be done. So when you do the training in a pruning aware way, the performance is going to decrease. It's going to decrease compared to the original one, because you are doing the training in a way that is not very optimized for the result, but is optimized for pruning. So because you're gonna do the pruning, so the performance is gonna drop. But once the training of the network is done in a pruning aware way, what you can do is like you can prune it. So depending on the threshold. So if you talk about the parameters, so let's say you use the threshold to do the pruning for best normalization scaling factor. So everything above this threshold is gonna survive. Everything below this threshold is gonna be pruned. And you do the pruning, and then you fine tune for 10 epochs. So the performance is going to be like 60.4, which is definitely not good. But like if you just increase the number of epochs and do more fine tuning, the performance is pretty good. It's almost close to the original one. Like this is like 70, and the original one was like 71.9. So it's very close to the original one. But the performance is like less than 1%. But in terms of parameters and in terms of flops, think of flops as the summation of all the multiplication and addition operations that happens in the neural network. So So if you think in terms of a number of parameters, the parameter in the original model was 3.6 million. It came down to 2.69 million, and in terms of the number of operation, they were like 4.67 gigaflops, and then it came down to 3.79. So for pruning, like the number of parameters and everything was reduced greatly, and this thing, the gain here is very substantial, and you are getting this gain just for a drop of 1%, like less than 1%. So for example, in my case, I think this is a really good result. Like I'm getting like almost half a model of the original size with less than 1% decrease in accuracy. I think like this is great model for me. I can just take this model and then deploy it like for my device. So this is what pruning can really give you. It can dramatically reduce your number of parameters and gigaflops. Okay, so and after this, okay.
Like we have about 10 more minutes or even less. Can we do as for that?
Okay. All right. Let me go quick then. Okay, so and then after this, there's something called like knowledge distillation. So now what happens in knowledge distillation is like it kind of distills the important knowledge from a bigger model, which here is called the teacher, to a smaller model, which here is called the student. And you can just use like knowledge distillation as a compression technique, like take a bigger model and then do knowledge distillation to get a student model, a smaller model. This itself is kind of compression, but like we did not use knowledge distillation as a compression technique. We actually use knowledge distillation as a regainer, because when you have a model, you do the pruning, there is going to be a drop in accuracy. The drop is going to be there in performance. So instead of just like fine tuning it like in a normal way, what you can do is like you can use knowledge distillation to do the fine tuning, because you have access to the original model as well. So you can use this thing as a teacher, and this can also help help in training of your pruned model. So this is actually better than just doing fine tuning. So my personal experience was that it always, most of the time, like 98%, I would say 98% of the time, it gives like better result than just doing normal fine tuning. So I would actually recommend you to use KD as a regainer instead of like a compression technique. So the way you can do KD is like either you can do KD in terms of output-based KD, or you can do like feature-based KD. So in what happens in output-based KD is like just the output are taken from the bigger network to the smaller network, and the loss is computed just on the output. And this is like KD for output. And in feature-based KD, what happens is like the similarity between the features of the two networks, they are compared. And this is how the KD is done in feature-based KD. And then there are cases where they actually combine both of these, like they're doing KD, also taking the output, and also, you know, kind of comparing the feature maps of the two networks. So you can do that too. Which one is good? It again depends on some models. Like for example, YOLO V5, this feature-based KD is not good. Like output-based KD is like way too good. So it depends. You have to experiment a lot to find like which one is good for your application. And then there is something called quantization. So quantization is about reducing the bit precision to represent parameters and or activations. So, you know, our original AI model is always like 14.32, but you don't have to always use 14.32 to represent the parameters of your model. What you can do is you can take it down to floating point 16 or even int 8, you know. So like you can change the precision of your model, and that thing can happen like in terms of this. You can just do the quantization for the weight parameters, or you can do the quantization for the activations for the feature maps, you know, or you can combine. You can do like parameters, weight parameters, and activations. So yeah, so they're like different ways. Like this thing totally depends on you. So if you talk about quantization, you will hear this thing a lot, like uniform quantization. Just like the name says, you know, the quantization, the bit precision like in the network is the same throughout the network. So if like from layer 1 to layer n, let's say everything was like floating point 32 in the beginning, you do uniform quantization, and then because it's uniform, like everything of maybe might go to like floating point 16 or int8. The important thing is like every layer, like every parameter should be in the same bit precision. Whereas in mixed precision, just like the name says, it's mixed. So some layers, some parameters are like in floating point 32, some are in floating point 16, some are in int8, and everything is mixed. Okay, so quantization can also be broadly divided into two categories. The first is called post-training quantization. So what happens in post-training quantization is like, just like the name says, the quantization happens after training, post-training. And quantization also decreases the performance. Like once you quantize your model, the performance is going to be decreased because, you know, the bit precision is changed, and that changes the, you know, activation range. So in PTQ, you can actually regain most of the dropped performance due to the quantization by using something called calibration data. So calibration data is a subset of your training data. So you can use a subset of your training data to do feed forward in the using the quantized model, and that will kind of help you to match the activation range of the original model, and this will regain most of the performance drop that happened due to quantization. So this is post-training quantization. So in QAT, which is quantization await training, this is actually similar to like pruning await training. So you are doing training in such a way that it's going to help you later during the quantization phase. So in what happens in QAT is like, you know, when the forward propagation happens, they actually do it in not in floating point 32, but in less than floating point 32 bit. So for example, maybe you are doing the feed forward in like int8, so int8 bit. So because the feed forward is done in int8 bit, that is gonna reduce the performance, and that performance can be represented in terms of loss, and that loss is also added to the training loss, to the network's original loss. So this loss that happens due to quantization is actually already included in the training process. And the neural network, because the training is done in such a way that the loss is always reduced. So this actually helps you when you actually do quantization where after the training, because in the feed forward part, it is done in such a way that it is done in less than floating point 32 bit. So the network already knows when something like int8 comes in like this, you know, the output has to be like this. So this is actually robust to quantization and actually gives you like better performance. But I actually tried like both. I mean, of course, QAT is a little bit better, but it is not like a way better. Like it's not dramatically better than PTQ. So I would recommend like PTQ for most cases. And I actually brought like few tables like from TensorFlow blog. So this one was about MobileNet V1. So in 14.32, the baseline accuracy was like 70.95. And this thing, the quantization that was done like after training, it kind of decreases to 69.5. And the quantization that was done, you know, during training, it kind of is, the performance is like 69.97. Of course, it is a little bit better, but as you can see, the gain in this part is not dramatic. I would be very satisfied with this part, and it's the similar for Resident V2 instead of V3. And the main speed up thing about quantization can be seen on the hardware, like on a CPU. Let's say the floating point, you know, it's gonna be like this. The quantized version of this model is like super fast for all the cases. So I took this thing from like this TensorFlow blog. You want to read more, feel free. Okay, so these were like the main techniques, and you might ask, like, is there a way to combine these techniques? Yes, there is definitely a way, but like, which is the best way? It kind of depends. Depends on the model, depends on the application. In my personal experience, you have a model. The first step that you do is like either you do tensor decomposition or pruning. You have to actually like do both to see like which one is better. So do both, and then it's because of the pruning, there is going to be reduce in performance. You can regain that drop by doing KD using the original model, and then finally you do the quantization, and then here you go to the next step. So this, if you follow this pipeline, this should give you pretty good lightweight model. So I would actually recommend you to do this unless you have some better ways. And the things that you can use to do compression is like there are a lot of like open source repos that you can use. This is something called Razor. This came out recently from like Detection Lab. So this covers all the detection repos. So this is pretty good. And AIML is a compression toolkit released by Qualcomm. It's also good, especially their quantization algorithms are pretty good. And then there's something called Microsoft NNI, came from Microsoft. It's also pretty good. And of course, Google has its own TensorFlow version of model optimization. This is good too. And this is for like text pruner. I actually never use it, but this is like good if you're into NLP. It helps you to prune transformers. And for me, like personally, the thing that was really helpful, because I am a PyTorch guy, I use PyTorch most of the time. So torch pruning was like very good for pruning. So you can take a look at all of these. I would recommend you to take a look at all of this. And finally, there is something called neural architecture source, NOS. So what it does is like it kind of it sources the architecture, the neural architecture that is good for your applications. That satisfies the constraints. So you can do source in such a way that you can kind of you can tell the sourcing algorithm the constraint. Okay, I want the performance minimum to be like this. Let's say minimum 80%, but I want latency like to be minimum like than this. So the sourcing is done in such a way that the performance is always maximized and the latency is always reduced. So this constraint, you can put it in the sourcing algorithm, and then you can also define the source space. And the source space could be like some lightweight models, for example, like ShuffleNate. ShuffleNate is one of the popular mobile architectures, and the modules that are way used in those architecture is really good. So you can put in that. You can take some modules from MobileNet. You can put in that too. So you can define your source space, and it's gonna sample like the searching strategy is gonna sample an architecture from your source space, and it's going to train and it's going to estimate. And if the performance and latency is satisfied, you get a really good lightweight model. So this is like another way of like finding a really good lightweight model. So you might ask like which one is the best way to get a lightweight model, because ultimately compression, what gives you what you get at the end is a lightweight model. So you can take a big model, use the compression techniques to do the compression and get a lightweight model, or you can just use NOS and get a light model. Which of these is better? This one is better, or this one is better? In my personal experience, if you have like enough time and computational resource, NOS, like a neural architecture search, is always better, because what happens here is like the hardware constraint, like by using the compression algorithm, the hardware constraint is not always taken into consideration. But for NOS, the searching is done in such a way that it is always taken into consideration. So NOS, I think, is pretty good, especially like if you go for more complex tasks like detection and segmentation and like pose estimation. NOS, I think, is a better option than just using the compression techniques to do the compression. Okay, so this one was pretty much the end of my presentation. I have a list of really good resources. If you want to learn more about on-device AI and model compression, I would recommend you to take a good look at these repos, this book. So this might be a good starting point for your on-device AI journey. And that was the end of my presentation. We go to Q&A.
Okay, thanks, Vivek. That was really helpful. There's one thing I wanted to add before we go into a question and answer session, right? The thing about the compression and the optimization is that it is not just for document like device part. Sometimes when you have a machine learning model like that is trained on PyTorch, and you have a model like that is just 1 GB, right? And you want to make sure that like you want to deploy that into a CPU, or you want to deploy it into your computer for ROI, then you can even use during that phase. Because in Doximo, what we have done is that we have taken PyTorch model that was just like 1 GB, and it needed a GPU to do deployment. But the matter of the fact is GPU is very difficult to come by, and there's no ROI on that, right? So we converted, we use compression technique, optimization technique, and then we deployed it on the CPU with a lower latency, right? So all the topic that Vivek has talked about, it can also be applied for any machine learning algorithm. And second important thing is that there's no silver bullet, right? You cannot just say that, oh, like this model would work really nicely on Pruning, will work on this the kind of model. No, in our case, sometimes for some machine learning model, the pruning has given also very good accuracy. There's no accuracy drop. Sometimes the quantization does really drop. So this is like like Bibek told that slide where you show that, oh, first you do this, and you try. So make sure that you always remember there is no silver bullet for all the problem. You Once you know the technique, you can try various method, and for your method, whatever works, is always better. And on top of this, like what Vivek said at the beginning, we were only focusing on the optimization, like the compression, but there is also part optimization. Example, using Onyx or other model might be a lot better. So make sure that compression is one part, but during your free time, that optimization part, we did not talk on this one. Go through that, because sometimes you might not want to do compression, but optimization itself might help you, right? So that is just the thing that I wanted to put out, so that you guys have a complete picture, overall picture over there. uh, so we have questions on the chat, so I'll go one by one. And one more thing is that we have taken this question and also put in ask me, ask for help. So if someone else has a because some of these are not related to this topic, right? These are not related to this topic, so because of that, if we are not the expert, I have put it on the ask me anything. So if anyone has a better answer than one we might have been giving, please do answer it over there also. And after this talk also, if we find better resources, we'll put it over there, right? So let's go from top, right? So the first question is from first question that we have is, how development of quantum computation might help AI ML. So Vivek, do you have any
Okay.
thought on that?
Yeah. Okay, so okay, this is like a little bit not directly related to model compression, because quantum computing, and just like the name says here, it is like next phase of computing. Because right now, we're using like GPUs and all those things, like the like chip-based computers, but like this quantum computing, it's just gonna take this computing power, computing capacity to next level. So the way it's gonna help is like we're gonna train models like really fast. Like for example, let's say if your model today, it takes like with the computing resources that we have today, let's say it takes like let's say 1 week to train. With quantum computing, you can do it maybe like in 1 hour. So it's things will speed up as the computing capacity gets better and better with quantum computing.
Okay. I think this was asked by, if I'm not wrong, it was asked by who had asked that question? Just give me a second. Yeah, Bhimachan, right? So I think he has left, but like if anyone has follow-up questions, they can unmute themselves. So I'm allowing people to unmute, so you can directly ask also. The second question that we had was what is the roadmap for writing our MLDL paper, right? So if you can have any thought, I think this is going to be a big topic. So
Right.
we'll also put that resources on the ask for help. But yeah,
Okay.
Vivek, what's your thought on that?
Okay, so my personal experience is that first you need in order to write a good MLDL paper, first you have to like narrow it down, like which area of ML or DL you are interested in. Like for example, let's say for my case, it's like model compression, but I have to narrow it down further. Like in model compression, what I'm interested. Let's say for example, pruning. So okay, I'm interested in pruning. So then what I would do after that is like I would like look for the state of the art papers, and I would read a lot of papers. But like when you're reading it, you are reading the things that is like already published. You are kind of reading like other people thought, okay, they thought like this, and then they verified their thought with the results. So one good mindset that I would recommend to have is like when you're reading the paper, okay, what if they did it like this? What if I do it the other way? What if I change this, or what if I add this, or what if always ask questions like what if. So because if you read this thing, like read a paper with this mentality, at some point you will definitely get, oh, like, okay, what if this, oh my god. So you have something, and then you Google it up, and you realize that nobody has done it before. So that's where it really starts. So now you have to do a lot of experimentation, make a lot of hypotheses, and verify your hypothesis with experimental results. And if the results are good, you are on your way to write a good paper.
Okay, awesome. So there is third question. Is there any de facto standard practice to avoid the loss of importance or relevant feature while implementing a pruning process?
To avoid the loss of important or while implementing the pruning process, de facto standard practice to avoid the loss of important or while okay, so the pruning like the pruning is done in such a way that the important and relevant features are always alive. I mean, they are never lost. Pruning is about removing the less important, less relevant features. So if you are doing pruning, ultimately, like those important and relevant features are always there. Are always present in the network. They do not go away. What you are doing, what you are removing, is the less important, less relevant features.
Yeah, I think one more thing over there, I think some of the algorithm that we have shown, like that also depends upon the algorithm. The main job of that algorithm is to figure out which of these are important and relevant,
Important,
right?
right?
So that algorithm might automatically handle. That is also one of the reason when we said at the beginning, there's no silver bullet. Sometimes some of this
Right,
algorithm
right,
will not work for your model, right?
right, right.
But yeah, so that is how like you are supposed to like not lose the important and relevant feature. The next question we have from Susil is, will there be any adverse effect if we use dropout with iterative pruning?
Okay, actually, this is a really good thing to ask, to be honest, because dropout in some way can be seen as training the network in a pruning aware way. Because like what dropout does is like it prunes like few of the parameters during the training randomly. So you can actually see dropout as a pruning algorithm, like as a type of like pruning algorithm. Actually, there is a paper about it too. So like I did not experiment like very detailed like with dropout and iterative pruning, but my experience was like I had an idea, like for example dropout, what it does is like it drops out like parameters, like certain number of parameters depending on the pruning, depending on the dropout ratio randomly. So what I did is like I kind of like fixed that randomness. So like every time like a set of parameters were dropped, and they were not dropped randomly, because I fixed that randomness, that thing were dropping like the same number of parameters, the same parameters every time the network was training. So those parameters were present in the network but were never involved in the training process. So when the training was done, you can actually remove those, you can actually prune those networks, because those networks were not involved in the training process. They do not have any effect on the performance. So I actually did like this thing, this experimentation. The results were pretty good, but what really happened is like while we were like in the process of writing a paper, I mean, there is a lab like in Canada, and they published a paper with similar idea. So yeah, that was the case. We did not try with like iterative pruning, but we only tried like one-shot pruning. But I would imagine like this will not have an adverse effect. It will actually help you to prune better.
Okay, so there is one more question that was sent directly to me by Robin. Can we use combination of this module compression method?
Yeah, yeah, definitely you can use it. Like you can maybe like even in the pruning you can combine a lot of pruning criteria. You can start with pruning by one criteria and then take the pruned model and then prune it with another criteria. You can do that. Yeah, definitely you can combine pruning. You can combine knowledge distillation. You can combine a lot of things. Yeah, you can definitely combine it.
Sure. I think that were the questions. Do anyone of you guys have any other questions? You can directly ask by unmuting yourself because you are allowed to unmute. So yeah, we can wait for like about 30 seconds if anyone has. Um, yeah, for those people, like on the like there was one message regarding Slack channel. So all of you guys, like some of you guys have been invited into the Slack channel, and some of you guys might not have been invited. There's a reason for that. What we'll do is that we'll send you a detailed email regarding that. We had our internal discussion because we have started last week only, so we are still in process of adding more people. So we, for those people who have not been added into Slack channel, what we'll do is that we'll send you a detailed email regarding what is a path for getting added into Docsum or like channel, Slack channel. The thing about Slack channel is we want it to be a bit tight knitted community of data scientists, like who have at least one project on data science, right? Because otherwise it will be too many people, too many noise and things like that. So what we'll do is that we'll send you a detailed email If you guys are interested on joining the Slack channel, then there are a few steps to be done if you guys have not done any data science project. So if you guys send us a link to a project that you have done on data science, or if you don't even have that, we have some steps to be taken which can be completed in 2 or 3 hours. So what we'll do is that we will we'll let you know on that, and then after you guys complete over there, we'll make sure that we add you guys into the Slack channel, right? Okay, so any other questions that that you guys have? Okay, Bibek, thanks a lot. This was super helpful to us. One more thing for all of you guys, please there's a feedback form that is circulated on the chat also. Manisha, can you also put that into the Slack channel so that people can provide the feedback over there? Please do provide your feedback over there so that we can make because we have 4 sessions for this batch, right? So we have 3 more sessions to come, then we'll have a break of about 2 weeks, and then we'll have 4 more sessions. So for that reason, we need your feedback. We want this to be interactive. We want to make sure that we bring the topic that is more relevant to you. So on the feedback form, you can put even that information regarding how would we have done it better. Was talk a bit longer or anything, right? So whatever you guys think will make this session more interactive, we want to do that. So please do provide your feedback over there, because that is how this community is going to grow larger, right? Thanks a lot for your valuable 1 hour, right? So hope to see you on the next webinar that will be on the Devanagari, it is of Devanagari in currently Quantization of Devanagari in Nepal, right? So hope to see you there, and hope to see you more interaction on Slack channel. For those people who have not been added to Slack channel, please click on join the community. Send that. Once that is done, either we'll be adding you to the Slack channel, and if because of some reason we're not able to add you, then we'll send you a detailed email regarding how we can be added, right? So please go through that step, and then hope to see more of you guys on the Slack channel, more of this collaboration, so that we can learn from each other.
And Bikram, let me add something at last.
Sure.
Just a gentle reminder what Bikram has mentioned before. If you are interested to present any talk, methodology, what you have done in the Kaggle or something like that, please reach out to us. We'll have a call. We'll go through your work and quality of the work. We'll assess them, and we'll arrange time to present in the community. We are learning from you, and we are sharing among us what we know. So just reach out to us to make sure that you can present. That is how we can reach out to larger audience about your org and your contribution to the AIML community. Thank you.
Awesome. Have a nice day, guys. Thanks a lot for the time.
Thank you so much, guys, for coming, and I look forward to connect with all of you.
Okay, bye, guys.
So if any one of you have not received the email regarding how to join the community, even after filling the form, so please mail me at manisha@aimlnepal.com.
Okay, awesome. Bye, guys.
Bye, everyone.
Bye.